So one of the problems that students found problematic for this homework was 950. So I think for today's review session, I want to work through 950. This is a bit of a long topic, so we spent about 2 weeks covering it. And pretty much we did a little bit of theory the first day and then just examples from then on. I think this was a good example to look at because we're looking at a three-dimensional object in three-dimensional space. And yeah, so I guess for today's review session, I'm going to try to work through problem 950. So let me just give me a second to draw the diagram for this problem. Now we have a three-dimensional Cartesian space. So I'm going to have my x-axis, my y-axis, and I'm going to have a tetrahedron on that Cartesian plane space. So my x-axis actually extends all the way to here. I'm going to extend my y-axis as well as my z-axis. So in this problem, we are given this tetrahedron. It is essentially a triangular pyramid, right? It's a pyramid. It has, you can see that the base has three sides, and then it's going to have three walls. This first wall, which is delineated by the black lines. But then you also have another wall and then a third wall. So this is actually the wall that's closest to you. And then these three walls are behind this wall. That's kind of, I think that's about the best that I can draw. But if you don't understand the drawing, you can always check the textbook. We're given some dimensions for this tetrahedron. We're told that the x dimension is A. In other words, this dimension is A. This dimension, which is the y dimension for the tetrahedron, is B. So that is this length. Then the z dimension is C, and that is this length, this height. Now, given that information, we would like to find the z coordinates of the centroid. Now, there's a couple of things to note here. Whenever we're dealing with two-dimensional areas, I always tell my students to make sure they know the limits of their area. Maybe they can find expressions for the curves and the equations that delimit that area. And the same applies for three dimensions, right? We want to make sure that we know the limits of this volume, of this body. Now, how we express those limits, we can use an equation for a plane. We can use equations for lines if we want. But I think it's best if we try to start to solve this problem. And then based on how we're solving it, then we can determine how we want to relate these planes or lines to each other. So let's just start the problem. We know that for every centroid problem, the first step is to set a differential element. Let me draw it right here. Set a differential element. Now, for one-dimensional problems, our differential element has a really, really small length, L, dl. For two-dimensional problems, our differential element has a really, really small area, dA. What about for three-dimensional elements? Do you know what dimension would this element have? So for one dimension, it's dl because it's a length. For two dimensions, we're dealing with an area, dA. What about for three dimensions?
dV.
Yeah, a volume dV, that's correct. So for our differential element, we'll have a differential volume dV. And we can locate this differential element at some arbitrary point, x, y, z. So we're going to locate our differential element dV at some arbitrary point x, y, z. Now, in two dimensions, we mentioned that we have two different ways of drawing our element. You know, in two dimensions, we could do an element that's very, very thin and horizontal, or an element that's very, very thin and vertical. So we have the same issue here in three dimensions, the same options here. We're going to have an element that's very flat, but we can orient that flat element however we want. We can orient the element maybe in the direction of this wall. We can orient it horizontally, so in the XY plane, or we can even orient it vertically in the XZ or in the ZY plane. Now, the book actually gives us a little bit of a hint, right? It tells us to set an element that is oriented in the XY plane. So in other words, we're gonna set a differential element, a tiny, tiny, tiny element that is actually parallel to the XY plane, okay? So this element parallel to the XY plane can be located at any arbitrary point. I'm just gonna call this my arbitrary point, X, Y, Z. And we're gonna essentially draw this element like we're taking a slice, like we're slicing a horizontal plate off of this element. This horizontal plate is parallel to the XY plane. So that sliced element would look something like this. So this is the element that we are slicing that is parallel to the XY plane. Of course, the element, it's not an area, it's a volume. So in order to have a thickness, we do need to assign it a very, very small thickness that we're gonna call dz. So you can see this element here. It's going to have a length x, a width y, but then a thickness in the z direction of dz. The length and the width are finite, right? They are countable, they're measurable. But the thickness is dz, which means it's a thickness that's so small that we can't even quantify it, okay? So we have this element. And just so that you have a reference, the element will have dimensions of x, y, and then dz. Okay, that is our element. If you look at this element from the top, if you stand on the z-axis and look down on the element, essentially you're gonna see a triangle, right? It's actually a triangular plate because it has a thickness, but it is that is what the shape, right? It's a triangle. Now, after we've set our differential element, the second step that we usually follow is to find the centroid of the element. So typically we want to find the coordinates of the centroid x squiggly, y squiggly, z squiggly. But here we only care about finding the z coordinate of the centroid, right? So the problem here is to find z bar. So because we only need to find z bar, then I really only care about finding my coordinate z squiggly. Now this element is located at an arbitrary point x, y, z. And now my question is, how is the z coordinate of the centroid of this element related to that arbitrary point x, y, z? So for starters, this element is a triangular shaped plate. If we were to stand on the z axis and look down, so if we're standing on the z axis and we look down into the x, y plane, essentially the element is going to look like a right triangle. And because it looks like that when we're standing on the z-axis, we know that its centroid will be somewhere at 1/3 of the base, 1/3 of the height. However, these are my x and y coordinates of the centroid. Here, I really care about my z coordinate of the centroid. That z coordinate is that vertical distance, right, between the xy plane and the centroid of the element. Now, because the element itself is located at a point x, y, z, that means that the z coordinate of the centroid z squiggly has to be located at a point z. So this step was pretty easy, right? We know that the centroid z squiggly is located at z. Because we don't need to find our x and y coordinates, we can just leave this step as it is right there and move on to our next step, which is to express the volume of this element. So we're going to express our differential volume dv in terms of our differential dimension. In this case, our differential dimension, you can see here, is dz, right? Because that's what we're going to integrate over. So we're going to express our differential volume dv in terms of dz. So let's see what that looks like. Our differential volume is dv. And in this case, we know that this triangle has a dimension of x and y. And we know the thickness of the triangle is dz. So given that information, these dimensions, x, y, and dz, can you tell me what the volume of this element would be? What do you think the volume will be?
The volume, the integral from c to 6, 1/2 times xy dz.
Exactly, that's exactly right? The volume would be 1/2 of x, y, dz. I know you mentioned the integral as well, but we will get there, right? We're gonna get to that part. But this dv is just 1/2 xy dz, just like you said. Now, what you're talking about is the volume of the entire thing, right? If we integrate over the entire thing from 0 to c, then yes, it will be the volume of the entire tetrahedron, okay? So we found our volume, and our fourth and final step is to integrate. However, before we even jump into integrating, we need to understand one thing. X varies if z varies, right? It's not a constant. Y varies if z varies. It's not a constant. You can see that if I were to draw my element a little bit lower, both my x and my y's would have been bigger. If I were to draw my element higher, my x and my y's would have been smaller. That means that with a change in z, we will have a change in x and a change in y. So now that the idea is to find a relationship between z and x as well as z and y. And here's where we come into our general line and plane equations. So you can see here that what we have here is essentially a straight line that tells us how x will vary with respect to z, right? In this straight line, we don't care about y. Here, y equals 0. So in this straight line tells us how x varies with respect to z, which means that we can actually write down an equation for this line. This is just a general line equation. And if we want to find a relationship between z in terms of x, we can say that z here is equal to, this is a linear equation, it's a line. So we find the slope. The slope is the change in y over the change in x. Here in y, the change is negative c, and in x, the change is a. So here my equation will be my slope, which is negative c over a times x, plus the intercept. So when x equals 0, the intercept is this point in c, which is c. So this is a general line equation, right? Slope times variable plus intercept. And we can do the same thing on the other side. We know that on this equation, this line shows us the variation of z with respect to y and nothing to do with x, because here x equals 0, so this is z with respect to y. So we can come up with an equation for this one as well. We can say that z equals the slope. The slope will be negative b over a, right? Change in, negative c over b. There we go. Change in your z-axis over change in your y-axis, because it's going downwards, it's negative, multiplied by my variable, and then plus my intercept, which again is c. When y equals 0, z equals c. And I wrote x here accidentally. I should have written y here. I don't think this is kind of clear. Let me rewrite these equations a little bit clearer down here. We get that z equals negative c over a, x plus c. And we also know that z equals negative c over b, y plus c. And now we know that we have a volume equation here, and we want to express this x and this y in terms of z. So we have two equations that relate x and y to z respectively. So we can solve. Solving for x, and here I get that x equals a over c times c minus z. And solving for y here, I get that y equals, and this is just solving, right? Just solving arithmetically for y. Here y equals b over c times c minus c. And now I have the relationship that I can apply into our volume equation. So our volume equation becomes 1/2 of x, but we know that x equals a over c times c minus z. So I'll just say a over c times c minus z. And y, but y equals b over c times c minus z. So b over c times c minus z, and then of course my dz. So that is my volume, my differential volume, the volume of that tiny element, okay? And finally, the fourth step is to integrate, as you already know. We know that the z coordinate of the centroid z bar is found by integrating z squiggly over the volume over the integral of the volume. And this is what Ryan was saying, right? The integral would be evaluated from 0 to c. So let's look at what that's going to be like. We have our integral, and we're going to evaluate it over dz. So the limits are the lowest point in z and the highest point in z. In this case, the lowest point in z is 0. You can see here. But the highest point in z is the letter c. So we're going to integrate from 0 to c, z squiggly. From step number 2, we know that z squiggly equals z times dv. And from step number 3, we found that dv equals 1/2 a over c, z minus z, b over c, z minus c, dz. I'm going to try to simplify this a little bit. I can say this is 1/2 a times b over c squared. So a, b over c squared, if I'm not correct, if I'm not wrong, I forgot the 2 for the 1/2, times c minus z squared, right? Because I have c minus z times c minus z, that's c minus z squared, times dz. On the denominator, I have the integral dv, so the integral from 0 to c of a, b, 2, c over 2, c minus z squared dz. And now I can integrate. Because we're going to have to multiply this by z, I want to make sure that I'm going to try to expand my equation. So I can expand this relatively simply, right? I have z bar equals the integral. I'm going to take out all my constants. These are all constants, right? So we can move them out. So ab 2c squared times the integral from 0 to z. And then I have z times, and if I square this term, I'll get c squared minus 2cz plus z squared times dz, if I'm not wrong. On the denominator, I'm going to take out these constants. Remember, these are all constants, so I can take them out. A, b over 2c squared. Integral from 0 to c. And then I get c squared minus 2cz plus z squared evaluated at dz. And now I can integrate. I think I can integrate relatively easily. Notice that we have a over a, b over b, 2 over 2, c squared over c squared. All this cancels out. Then my integrals are simply the integral of z c squared. C squared is a constant, right? So this should be c squared over 2 z squared. I have the integral of c squared times minus 2c. Minus 2c is a constant. So this would be minus 2c over 3 z cubed. And I have the integral of z cubed. So that's 1/4 z to the power of 4. And all of this is evaluated from 0 to c. I have my integral of c squared. So that will be just c squared z. I have the integral of negative 2cz. So that's negative cz squared. And I have the integral of c squared, which is 1/3 z cubed. And all this evaluated from 0 to c. We can start to notice some trends here. C squared z minus z squared c, that cancels out, that's 0. And notice that I have a couple of common terms here. But first, I would like to evaluate it, okay? So if I evaluate it, I have replace all the z's with the letter c, replace all the z's with 0. And this will give me z bar equals 1/2 c to the power of 4 minus 2/3 c to the power of 4 plus 1/4 c to the power of 4. All this divided by 1/3 z to the power, c to the power of 3. And then we can just do a little bit of math manipulation. Notice that we have 2, a 3, a 4. We can find a common denominator at the number 12, right? So I multiply this by 6, and I get 6 times c to the power of 4. I multiply this by 4, and I get 8 times c to the power of 4. And I multiply this by 3, and I get 3 times c to the power of 4, and all of this will be divided by 12. Of course, in the denominator, we have 1/3 c to the power of 3. 6 plus 3 is 9 minus 8 is 1, right? So we get c to the power of 4 divided by, here I have 12 over 3, that's 4 times c to the power of 3. And this eventually, notice c to the power of 4 cancels out with c to the power of 3, and this will finally give me my answer of c over 4, which is the z coordinates of this centroid. So you can see that even though it looks like a challenging problem, as long as you know how to relate your 3 dimensions, how to relate z to x, and how to relate z to y, all of the other steps are pretty much the same, all the steps that we've been covering so far in this class. So are there any questions before we wrap up this review session? All right, if there are no questions, then I'll see you next week. Try to make sure you finish your homework for centroids. And next week, we'll start with a new topic called moments of inertia.